Hi, and welcome. If you ever wonder whether Kubernetes was the right place to run your production stateful application, and if so, how to do it properly, then you're in the right place. My name is Nick Vermandé. I'm a principal developer advocate with OnDat, and in today's talk, we're going to be taking a look at all the Kubernetes primitive that relates to stateful application and how OnDat can help you run them anywhere and at scale. So let's get started. When we look at traditional applications, there are mainly two factors that will determine how the application is going to behave. First, the code itself. If it has not been designed and implemented in a way that makes the application performant, resilient, or scalable, then it won't just happen magically. And the second factor is the underlying infrastructure. The discrete components such as compute, networking, and storage will influence how the application will behave. And here comes Kubernetes, with a substantial number of interfaces, standardizations, which makes the infrastructure appear as easily pluggable. And if done properly, it will unlock key benefits such as data mobility, consistent application performance, all aligned with existing Kubernetes benefits for developers and platform admins in terms of automation and continuous integration. This is exactly what we want to achieve with OnDat. But before moving forward, let's take a step back to understand what kind of application we can really run on Kubernetes. It all started with the advent of containerization, in particular with Docker, and how you were supposed to run containerized application and treat them as pets or cattle, or in other words, as mutable or immutable pieces of software. Well, the last 50 years of IT industry taught us that there is a sort of a race to commoditize platforms. And Kubernetes is the ultimate example. Although the race really started at the beginning of the 70s, where IBM released the first capability of hardware partitioning, which at that time was a sort of virtual machine. But it's not before the mid-90s that the web application framework really started to grow. Then VMware gave us this ability to industrialize x86 virtualization and run these web applications in a much more scalable fashion. But it's the adoption of public cloud with AWS leading the pack, together with software-defined infrastructure, that enabled the release of both software and infrastructure component on demand. Finally, Spring Boot brought us an opinionated framework to resolve many of the application dependencies, which ultimately helped the adoption of microservices and the DevOps philosophy, where immutability is one of the core components. But this was just the beginning. In anticipation of Kubernetes success, Google and the Linux Foundation joined forces to form the CNCF, or Cloud Native Computing Foundation. And in 2016, we see an acknowledgement that there's a need for some sort of ability to run application that require persistency as well as a stable identity. The alpha pet sets object, in reference to the animal, becomes stateful sets in beta and guarantees at most one pod for any given ordinal index. So this is actually a very good candidate to run applications such as message queues or databases that need to write data to disk, and this data need to be retained. But let's take a closer look at how stateful sets work. So to understand stateful sets, we first need to understand how deployments work, which is the object that is used for more traditional stateless application running in Kubernetes. In the context of today, what is important to understand about deployment is that they can be considered as cattle. They are replaceable, and when one pod fails and another takes its place, it will have a different name, a different identity. Another important thing to notice, as depicted here, is that when you attach a persistent volume to a deployment, it will be common to all pods part of the deployment. They will use the same storage place. As pods will most likely be running on different hosts, this means that a shared file system like NFS must be used, which obviously will have negative impact on performances. So applications like databases are not suitable for deployment or any kind of application that has a concept of primary and secondary replica. On the other side, we have stateful sets, or pet sets, the way they were initially called. At the very top, you can see that they are not backed by a traditional service. A headlet service simply involves that there won't be any cluster IP allocated or VIP to that particular application. Instead, every pod will have a full qualifying domain name managed by Kubernetes, meaning that it is well known in the cluster and that the pod can be reached using that name. Another property of pods part of a stateful set is that they will be allocated an ordinal number starting from 0 to n-1 for a stateful set with n pods. So for example, if pod 3 is deleted, the stateful set controller will make sure to recreate the same pod 3 with the exact same identity. It will be reachable using the same FQDN, although the IP will be different. And finally, the stateful set manifest makes use of volume claim template, which enables the dynamic creation of individual persistent volumes, one per pod. This makes sure that every pod can write in its own space and that a deleted pod will be recreated with the same volume attached. However, there are still challenges to be solved in that space, but more on that a bit later when we'll be talking about OnDat. So let's go back to our timeline to see how Kubernetes is evolving in the IT landscape. Public cloud providers have been innovating like crazy and introducing a bunch of new services with increasing granularity in terms of what can be achieved. Serverless is a good example, as it delivers function as a service and is of course backed by containers behind the hood. This technology also reached Kubernetes with the Knative project in 2018. Another proof that Kubernetes is now mainstream is the ability to add Windows nodes to run Windows containers. And with machine learning and AI becoming the norm, we've also seen the release of Kubeflow in 2020, which is based on Google TensorFlow model. So as you can see, the Kubernetes toolset is constantly improving and it's becoming easier to deploy any kind of applications in Kubernetes, really. Sometimes with close to zero effort, as we'll see later in the demo. But there are other patterns that will also help you build your data service layer in Kubernetes. Shifting left is certainly a common pattern that will help reduce the friction between developers and infrastructure admins, while also boosting your DevOps processes. But what is shifting left about? The initial idea is to test software very early in the CI pipeline and the software development lifecycle to detect and fix any issue before the code is actually deployed. In the context of Kubernetes, as it includes many infrastructure components, this means that they must be defined alongside the application code. So, for example, if you have some stateful set as part of your application, the data layer must be defined natively in Kubernetes in a declarative fashion and deployed without any manual intervention. The idiomatic way to do this in Kubernetes is, of course, by using YAML, which in our case defines infrastructure requirements. Also, by integrating natively with Kubernetes, you can now take advantage of all its features. So scale out with the cluster, extending the API, using custom resources while interacting with the cluster through standardized interfaces such as CNI for the network or CSI for persistent volumes. And this is exactly what OnDat is about. So OnDat is a cloud-native software platform that provides an ecosystem of features to manage persistent volumes for stateful applications. Our engine makes use of block storage locally attached to Kubernetes nodes and present an abstracted layer consumable by Kubernetes through the CSI interface. We do provide enterprise-grade features for the associated volumes, including synchronous replication, encryption, high availability, and optimum performance. But most importantly, the solution is really easy to consume as it is Kubernetes. So it can be integrated into CI pipelines and ultimately provides a way to include mission-critical application into this shift-left paradigm. As a best effort, we'll always try to collocate pods with their persistent volumes, but depending on the constraints, they'll also be allowed to access it remotely through our DirectFS protocol. Alternatively, you can also build cluster with dedicated storage or compute nodes, whatever suits your needs best. Now, another principle that will help you shift left is GitOps, which utilizes Git or any other version control system, really, as the single source of truth for both your application code and your Kubernetes manifest. Remember, to provide on-demand capabilities, you need to have both the application and the platform requirements expressed in a declarative format that represents the intent. Then it is the responsibility of the GitOps workflow to reconcile this intent with the finite state inside Kubernetes. So here is an example of how that would work. The main difference between a GitOps pipeline and a traditional CI/CD pipeline is the way the artifact is deployed. While in a CI/CD pipeline, the artifact is pushed to the destination, the GitOps pipeline introduces a component that is sitting inside the Kubernetes cluster. Its role is to continuously watch for changes on the configuration repo and apply them to the Kubernetes cluster. And there are a couple of benefits when doing this. First, no imperative command is never initiated on the cluster, which allows you to restrict access to that cluster, as well as reduces the attack surface and only authorize valid changes. Another benefit is that you can now leverage syntactic policy engine on the YAML file inside this repo to enforce compliance. So for example, as OnDat configuration is encapsulated in as YAML in that repo, it enables the enforcement of strict SLO on the data service layer. So for example, you can deny any change that doesn't have the proper number of persistent volume replicas or doesn't have encryption enabled. So besides automation capabilities, GitOps principles also allow you to improve control and in the end, shift compliance left. Now that we have described some of the Kubernetes pattern around data management and map them out to OnDat capabilities, let's take a look at what that means from a business architecture perspective. As OnDat is Kubernetes and also introduces new features required for running stateful application at scale, you can now move away from opaque and costly database as a service product and just run Kubernetes everywhere. Any Kubernetes distribution, any cloud, you will experience a consistent and standardized approach in deploying as well as operating your most valued applications. So in a nutshell, OnDat is adding a layer of abstraction in Kubernetes, sitting on top of your Kubernetes distribution of choice, and enabling the deployment of stateful mission-critical application in a very simple and elegant way. We believe we play a key role in this ecosystem because, let's face it, there's no such thing as a complete stateless application. So now, before jumping into the demo, I just wanted to give you a quick summary of the features that OnDat delivers. At the foundation, OnDat is a twofold solution. We have two distinct planes. First, there is the control plane, which is the brain of the solution, and then the data plane, which delivers the low-level data feature set. The control plane is responsible for managing the OnDat cluster state, implementing a consensus protocol, deciding on volume placement, and for this also extends the original Kubernetes scheduler. On the other hand, the data plane is responsible for serving the data and making sure all the features that you enable work properly. This includes thin provisioning, synchronous replication on a per volume basis, compression, encryption, caching, failure mode, fencing, and of course, all the features that we are going to release over time. But that's enough theory for today. Let's summarize what we've been discussing so far. So what are the 5 steps to free your data? First, use stateful sets in Kubernetes to run your stateful applications. Then shift left by adopting a Kubernetes data service solution, and adopt GitHub's principles to gain control on your operations as well as security. When using a data service that is Kubernetes, make sure to leverage enterprise-grade features, especially around security, resiliency, and scalability. Then finally, put your eggs into more than one basket. We know that the future of IT is hybrid, so don't hesitate to run Kubernetes clusters into various environments on premises, in the cloud. OnDat will have you back by providing a data service layer that is common to all your clusters. So now let's get our hands dirty by taking a look at a real use case. So the idea is to deploy a Redis cluster in less than 5 minutes by using a Kubernetes database operator together with OnDat. So the final architecture we want to deploy is the one that is currently displayed on the screen. This is going to be a Redis cluster with 3 leader pods as well as 3 follower pods. All the storage is going to be dynamically provisioned by the use of a storage class, which we are going to call replicated, and that will also specify a certain number of policies that will be applied to all the provision volumes. So dynamically, the storage class will provision persistent volume claim and persistent volume that will be individually attached to every pod that is composing that application. So without waiting any further, let's get connected into that console. Let's connect to our Kubernetes cluster and check out what has been installed there. So we can notice that the OnDat solution has been installed. Actually, it's using the StorageOS engine. So any component that is prefixed by StorageOS is part of the OnDat solution. We can notice that we also have a OnDat or StorageOS cluster operator, which is used to deploy the initial cluster just by using a YAML configuration file. The operator will monitor the Kubernetes API, and once the YAML file has been applied, it's going to create a custom resource in Kubernetes etcd. And based on that, the cluster operator will react by provisioning the OnDat cluster. The rest of the OnDat solution is composed of a couple of deployments. So we have the StorageOS CSR helper, we have daemon sets, and then we have a deployment, the API manager. And also for Redis, I've already installed a Redis operator that I've taken from operatorhub.io, where you can find a bunch of operators for databases and all the stuff. And the idea is you install the operator via Helm, and now this operator is going to monitor for Redis cluster custom resource definition, represented also as YAML. And when the operator seeing that a custom resource it's watching has been deployed on the Kubernetes API, then it's going to deploy in turns a cluster as defined per the YAML configuration. Now, let's check some of the components that are available after installing the OnDat cluster, starting with the storage class. So we can see that one storage class named fast is available after installing the OnDat cluster. Now we can get a quick look at it. We can do fast storage class, fast YAML. So we can see that there are no labels, or in that case, parameters that configure a certain number of replica or any other feature, which means that we're just using the default here, which is really 0 replica. Which is not necessarily what we want for our Redis cluster, but we'll still use that fast storage class so that I can show you how to modify it later. Let's also check some information that is directly available from the OnDat cluster, like, for example, the state of the cluster. We can see there are 3 nodes, all healthy. We can do the same with the volume. We shouldn't have any volume created in any of the namespace. So -A for all namespace. We actually map one-to-one a Kubernetes namespace with a OnDat namespace. So we can see that no volume has been created yet, which is good. Next, let's deploy the Redis cluster. So for this, we are going to be using Helm. And if you're familiar with Helm, you can customize some of the values it's going to be using by using the value.yaml. So I've copied it from the original Helm chart, and we can see that here we have some options, including the name of the storage class to use. So the Redis cluster is going to be composed of multiple pods. So we're going to see that there will be one set of leaders and one set of workers or followers. In that particular chart, they are going to use all the same storage class, which in that case default. But remember, we want to be using the fast storage class. So let's deploy with this. So now we can do helm install -f values, the name of the chart, and then the destination namespace, which is going to be Redis in our case. So let's proceed with this. All right, so it's been deployed. So we should see some pod starting to pop up in the Redis namespace. Okay, so remember, it's a stateful set, so not all pods are going to be created at the same time. It's going to be proceeding by order. So for a particular stateful set, we have one follower, one leader stateful set. If we do like a kubectl get stateful set in that particular namespace, you see there are 2 stateful sets. And before going to the next one, so the -1, the system is going to wait that the -0, so the previous one, is completely installed. So, which is probably not the case yet. Let's check. Okay, so we have actually 2 running. For the follower leader, we have 1 still creating, and we're going to have like 3 for each of the stateful sets. So 3 followers and 3 leaders. But we should also start to see some PVC provision. Oops, it's not PVD, it's PVC. Okay, so as the system provisions a new pod, you can see that dynamically PVCs are created with the volume of 1 gig as defined per the Helm chart, and which is the storage class fast. So now if I go back to the StorageOS command line and get volume in the namespace, you can see that all the volume, so 6 of them, has been provisioned, and we have 0 replicas at the moment. So although we are using the storage and the data layer provisioned by OnDat, there is no real replica that has been set yet. So now let's create a storage class with replicas. So for this, what we usually do is we just dump the storage class configuration for the fast one, save that into a file, and edit that file. Just change the name, replicate it, and add the parameter to have replicas. So it's simply storageos.com/replicas, and then just a number. We have 3 nodes, so we're going to have 2. And it's the same thing for any features you want to enable, whether it's compression, encryption, it will be the same format. So very simple. Now we can just kubectl apply this, and now we have a replicated storage class that has been created. Now, unfortunately, you cannot change the storage class of an existing stateful set that has been deployed. So what you're going to do is, if you want to increase the number of replicas of the volumes that are consumed by the pods part of a stateful set, then you have to directly interact with the PVCs themselves. So those PVC has been provisioned. So if I want to change the number of replicas, remember we have 0 replica for them, then I can just add a label for all of them. So I can do something like kubectl label here -n redis -- overwrite. So imagine I want, 2 is good. So let's do that. Okay, so we've done this for all 6 PVC. Now, if I, of course, they are still attached to the storage class fast, but now if I check my volume configuration on StorageOS API, you can see that now all of my pods, or the volumes attached to those pods, have now 2 replicas. So that concludes our demo for today and our talk too. I hope you found it useful. Maybe you learned one thing or two, and I'll see you next time.